Hi there, everyone. We're now on our last probability distribution that we'll learn in these lessons. Today we're going to learn about Poisson probability distribution. Poisson. It's not Poisson, by the way. Poisson probability distribution is a special type of discrete probability distributions. It's called Poisson because the one that discovered it is named Simon Denis Poisson or Denis. He's a French guy. This was introduced by him in a book he wrote regarding the applications of probability theory to lawsuits, criminal trials, and the like. This book, published in 1837, was entitled, you read that version, I'm going to read the English version, Investigations into the Probability of Verdicts in Criminal and Civil Matters. So let's call it Poisson, but if you're going to see the proper enunciation of that, pronunciation is Poisson because it's French. But let it be Poisson for now. That's the guy. So what is this Poisson distribution and Poisson process? So experiments yielding numerical values of a random variable x and the number of outcomes occurring during a given interval of time or even a specific region or space. So you know the occurrence already in a interval or space. You have that information, and you want to ask something. You know the probability of that happening again in that certain interval or space. So we call that Poisson experiments. The given time interval may be of any length, such as a minute, a day, a week, a month. So it doesn't really matter, but at least as long as it is specific, it is a specified time or space or region. So a Poisson experiment can generate observations for a random variable x representing number of telephone calls per hour, number of days school is closed due to typhoons, number of postponed games, specific regions, number of field mice per acre, etc., etc. Okay. So just some reminders of the Poisson process. A Poisson experiment is derived from the Poisson process, and possesses the following properties. Number one, the number of outcomes occurring in one time interval or specific space or region is independent of the number that occurs in any other disjoint time interval or region or space. So again, it's disjoint. It is independent of compared to those different um, time interval. The probability that a single outcome will occur during a very short time interval or small region is proportional to the length of the time interval or size of the region and does not depend on the number of outcomes occurring outside of this time interval or region. So if ever the time interval given and the one that you're asking is not the same, you just need to, since it's proportional, you just need to make use of ratio and proportion to make it of the same time interval. And number three, the probability that more than one outcome will occur in such a short time interval or fall in just a small region or space is negligible. So if it's more than one, actually there's no number of trials in Poisson processes. You only have one single variable actually in a given statement. So the number x or the random variable x of outcomes occurring during a Poisson experiment is what we call a Poisson random variable, and the probability distribution derived from this random variable is what we call the Poisson probability distribution. So the Poisson process, in the Poisson distribution terminology, the average number of occurrences in an interval is denoted by your Greek letter lambda, which is the average number, it's the expected number. The actual number of occurrences in that interval is denoted by your big X random variable. Then, using the Poisson probability distribution, we find the probability of X occurrences during a given interval of time or space or region that the mean occurrences during this interval lambda. So, what is the formula for our Poisson probability process? The formula is quite simple enough to read, but it has some constants that one needs to have a calculator to start with. So, the probability distribution of the Poisson random variable x representing the number of outcomes occurring in a given time interval or space or region is denoted by this formula. So the probability of your x given your lambda is equal to your e. E is the Euler's constant or Euler's number rather, sorry. I think there's another one for Euler's constant. Euler's number E raised to negative lambda times this term to lambda raised to x, your random variable, all divided by your x factorial, where x is a random variable from 0, 1, 2, 3. So that's your formula. The lambda is the average number of outcomes per unit of time or space, and E is your Euler's constant, Euler's number, which is 2.718281828. And that's the formula. That's how we use it. Okay, so given that your E is that, some sidelines or segues. So we have the E as your Euler's number. It is named after, of course, the king of mathematics or mathematicians, Leonhard Euler. And the constant was derived by as the Swiss mathematician, the same guy, Jacob Bernoulli, while studying compound interest. So um, remembering Bernoulli again, so he's the one that created the Bernoulli process. Okay, so he's the one as well, known as the one that first discovered this constant E, though it's named after Euler because Euler studied it intensively. Bernoulli was working on compound interests, and when you work out the number of times in a year, that's your M or J in some books. If you're going to make it infinity, your interest will not actually become infinite as well. There's a limiting value to that, and that limiting value is 2.71828. Okay, you set it all up. Say all of your values in your compound interest is 1, including the principal amount. Set your M to be number of recurrences per year. Make it infinite, and you will have, from your principal amount of 1, it will become 2.718, and that's your limiting value, and that limiting value has become E, okay, in today's standards. So that's Bernoulli again. So the Poisson probability distribution, let's have an example. It's quite easy to apply actually. It's quite simple enough. For example, on average, a household receives 9.5 telemarketing phone calls per week. So there are 9.5 telephone calls that will advertise something. What is the probability that a randomly selected household receive exactly 6 telemarketing phone calls during a given week? So the average here is 9.5. This is your lambda, everyone. So this one here is your lambda. So this is your lambda right here. It's 9.5. And you are asking the probability of getting 6. So this is your x. So if you're going to put this in the formula, it's going to be Euler's number E raised to negative lambda, which is 9.5. Let me write it down slowly. Then you multiply that by your 9.5, this whole term. Not anymore a denominator, not anymore an exponent, but a term here. Raise this to 6 all over 6 factorial. You just input that in your calculator, and then you will get the answer for this question. So if we're gonna make use of our online calculator, good thing it's there. So we have E. It's over here. It's standard in all calculators. It has an E. We raise that to negative 9.5, and then we multiply this by 9.5. We raise 9.5 by 6, and I forgot to put sorry. Let's do this again. Let's put a parenthesis first because it will denote that this will be your whole numerator. So your E raised to negative 9.5, close parenthesis, times 9.5 raised to 6 all over 6 factorial. Where's factorial over here? We'll do this. And then hit enter. Okay. And this is your probability of that occurring. 0.076, or that shall we say 7.6%, 7.64%. So if an average household receives 9.5 telemarketing phone calls per week, the probability that you'll have exactly 6 is 7.64%. Okay? See, I think there's no value here for the factorial. I think that will give you factorial. Let's try 5 factorial. It should be 120. Oh, that's correct. Okay, so I can use the exclamation mark. Okay, next. So in this example, we will read it first. A washing machine in a laundromat breaks down an average of 3 times per month. Find the probability that during the next month, the machine will have exactly 2 breakdowns. So 3 times in a month, that's the lambda. And the probability that we want to find is 2. So let's put that in the formula. So your Euler's number E raised to -3, that's your lambda, multiplied by 3 raised to 2 all over 2 factorial. Let's put that in our calculator. So we have, sorry, we have our E raised to -3, and oh, forgot. Start with the parenthesis. E raised to -3 times 3 raised to 2, close parenthesis, divided by 2 factorial, or just simply 2, right? Will be the same. So the answer is 22.4. So the rounded off 22.40 or 22.40%, meaning the probability that there will be 2 breakdowns this month is 22.40%. Okay, now let's jump ahead to our last example before we end this video. 10 is the average number of oil tankers arriving each day at a certain port city. The facilities at the port can handle at most 15 tankers per day. What is the probability that on a given day, 3 tankers have to be turned away? Again, 10 is the average number of oil tankers arriving each day at a certain port city. The facilities at the port can handle at most 15 tankers per day. What is the probability that on a given day, 3 tankers have to be turned away? So 10 is the average number. That's our lambda, 10. Okay. At most 15. So the maximum number that the port can handle is 15. So what's the probability that 3 tankers have to be turned away? So if we're going to analyze the problem, 15 is the maximum capacity of this port city to accept oil tankers. Now the question is, what's the probability that there will be 3 tankers that will be turned away because the maximum capacity has been reached? So if we're going to analyze, we're not going to make use of 15. We're not also going to make use of 3 as our x, but we're going to combine them. It's going to be 18, which is our x value. So our x is 18. Because if there are 15, which is the maximum capacity, and 3 have turned away, meaning in a certain day, 18 oil tankers arrived. Okay, I hope you get the idea of that. That's why we use 18. So we put that in our formula, E raised to -10, because that's our lambda, multiplied by 10 raised to our random variable 18 all over 18 factorial. Okay, so we input that in your number calculator right here. So sorry, E raised to, sorry, let's start with the parenthesis. E raised to -10. We multiply that by 10. We raise that by sorry, not -18, but simply 18. Apologies for that. Should not be negative 18. It should be only be positive. So it should be only 18. Close parenthesis, another close parenthesis for the fraction. Divided by 18 factorial. So we hit enter. And it will give us 0.00709. So that's simply, if you're going to round off to the fourth decimal place, it's going to be 71 or 0.0071. So the probability that three tankers have to be turned away is 0.71%, so less than 1%. So it's very unlikely to happen. Okay, or almost impossible to happen, but not really impossible because it's not clearly zero. Okay, so that's it for some examples for the Poisson. Let's end with this idea. Sorry, let's delete those. We also have the mean and variance of Poisson distribution. So remember, for the normal random variable, we multiply x and px to get the sum. For the variance, we square the x, we multiply it by the p of x, we get the sum, and then we minus it from the expected value squared. So for the binomial distribution, we have np for the mean, we have npq for the variance. And for the Poisson distribution, like I said, it makes things simple. The mean is equal to the variance, which is equal to lambda. Of course, don't forget that the SD of the Poisson distribution is the square root of lambda, not the lambda itself, because that's a variance. So always remember that the SD is equal to the square root of the variance. So right. And that's the end. Sorry, wrong one. That's the end of our lessons in probability distributions. Okay, and yeah, thank you very much. Thanks for listening. And yeah, I'll be seeing you in the next parts of our lessons. So we're done with probability. We will be moving ahead to inferential stats next time. So thank you very much.